Hi there. During this session I'm going to try and introduce you to the most basic of all climate models. This model goes under the assumption that the heat going in from the sun, if it equals the heat loss from planet Earth will keep a balanced temperature. So it will stay the same temperature. So this is the simplest of models. The formula we're going to be thinking about here is total power absorbed equals total power emitted. And what I'm going to do during this session is think about some of the issues to do with related to the total power absorbed side of the equation and the total power emitted side of the equations, which we've got to take into consideration while we're doing these models. So let's start off with the total power absorbed. The Earth is an absorber. Now, as we know, the Earth is obviously not a star, so that means it is not a perfect black body. So that means as an absorber, there's some issues. And to fix that, what we do is use a term called the albedo term. And this is introduced, it just depends on the type of surface. So even from this picture here, we can see there's lots of different types of surfaces. We have the frozen tundra of the north, we have acres and acres of ocean, and then we have the different types of surfaces we find on land. So the albedo is a term we have to take into consideration, and the albedo term is equal to the total scattered power divided by the total incident power. So it thinks about the amount of power which is scattered. Therefore, if we want to think about the amount of power absorbed, we do 1 minus the albedo term, which tells us how much energy is actually absorbed by planet Earth. So total power absorbed, if I take this into consideration, is the power emitted by the sun. The last session I spoke about gave me a value of 1,368. The area of planet Earth facing the sun, pi r squared, multiplied by a fraction of the sunlight actually absorbed by Earth, taking on board that albedo effect. Now, I know the area facing the sun is a simplification. We're thinking of it as a flat surface rather than the spherical shape that it is, but it's an assumption which works okay for now, okay, at this simple basic level. We think about the average albedo for Earth as 0.31. It's kind of a suitable average. If we look into more detail, we see that there's a range of different values depending on the surface, and as the Earth's surface changes due to the effects of global warming, then so does this overall average. So that may have an impact in the future. So that's one side of the equation to think about. Now let's think about Earth as a radiator. So again, Earth is not a perfect black body. So that means it doesn't perfectly follow Planck's theoretical black body model. There has to be an adjustment of some sort, and this is known as an emissivity term, and it's again introduced depending on the surface. So what we have is black, the power equals the area multiplied by Stefan Boltzmann's constant by the temperature to the power 4th, and this term E is the emissivity, and that depends on the surface which we're looking at. Overall, if we think about this as total power emitted, it's going to be power emitted per unit area times area planet times emissivity. Power emitted per unit area is going to be Stefan Boltzmann's constant times T to the power 4. Area of the planet, again I've simplified here. I've said that this is pi times r squared, which I guess is just the one-dimensional flat area of a circle with a radius of planet Earth. This helps in some calculations in a minute, but it's an acceptable assumption. And E is the emissivity factor. Emissivity on average for planet Earth is about 0.6. Okay. So now we have a formula for the total power emitted and a formula for the total power absorbed. This allows us to predict a temperature. So if power absorbed equals power emitted, if we do the calculations, we can see we know about all of these terms, and we can solve for the temperature of planet Earth if this model succeeds. Now, my simplified versions of the area means that quite quickly I can cancel out pi radius of Earth squared, pi radius of Earth squared from both sides. Then if I put in my numbers, I can then rearrange for t. Again, I've put in my numbers here. I've put in the Stephan-Boltzmann's constant in. If I rearrange, I get T4 equals that value there. And finally, if I find out what the fourth root is, I can discover that my temperature should be 72 Kelvin, which is, remember, in Kelvin, so that's the equivalent of minus 170 degrees, which is pretty cold. Now this is the key feature for this session. If we overly simplify our models for planet Earth, we get very, very low temperatures. We have to take into effect what is known as the greenhouse effect, and it's really, really important for giving us more realistic models. And that's what we'll be thinking about in more detail in future sessions.